Today, section 9.7, we're going to look at Taylor and Maclaurin polynomials. Alright, remember back in the good old days? Back when you were taking Calc 1? Long time ago. I might have given you a function. I wouldn't have given you the function f of x equals e to the x, because we didn't talk about e to the x in Calc 1. But I might have asked you to find the linear approximation, also known as a differential, centered at x equals 0. What did that mean? If I asked you to find the linear approximation to f of x equals e to the x, what was I asking you to do? Well, what do the words linear approximation mean? What's that? Limit? No limits. Linear means it's a line, it has a slope, that's correct. And what do I mean by linear approximation? Well, if I were to graph this, e to the x, what do I get? I get an exponential curve. I don't get a line, do I? But what I'm asking you to do is find an equation of a line that comes close to matching this e to the x function at x equals 0. To do that, we wanted two things to happen. So we want our line, I'll call it L of x, to be mx plus b. We wanted two things to happen. We wanted f at 0 to equal L at 0. And then we wanted f prime at 0 to be the slope, which is, of course, L prime at 0. All right, so if this is my function f of x, what's f at 0? F at 0 is going to be L at 0, which is 1. In this equation, mx plus b, which letter is L at 0? Not x. B. If I plug 0 in for x, I get 0 plus b. Isn't that known as the y-intercept? So that's the b number. So I want b to be 1. And then what's m? M is the derivative at 0. What's the derivative at 0?
1.
It's 1 also. So our linear approximation is going to be x plus 1. Okay, so there's our curve, and there's our line. Does that line do a good job of approximating that curve? No, why not? Okay. Does the line do a good job of approximating that curve? Close to 0, it's not bad, is it? If I'm close to 0, my line and my curve are pretty close for a while, aren't they? After a while, of course, the curve goes off and it's no longer good. But if I were to zoom in again, there's my curve, and there's my line. Does my line do a good job of approximating the curve? For a very short while. I mean, this isn't our window now is very, very small. It does a good job for a very, very short time. Well, it doesn't make a lot of sense, really, to approximate a curve by a line, does it? So what would be better? No? What would be better than a line? Maybe a parabola would give us a better approximation. All right, so we're going to repeat. We want f of x to be e to the x, and then we want to come up with a polynomial that approximates it. We'll use a quadratic equation to see if we can get a better approximation. Okay, and I want the three things to happen. I want f at 0 to be the same as my polynomial at 0. I want my first derivatives to match. And I want the second derivatives to match. So, really what I have here is I'm trying to find three letters A, B, and C. In order to find three letters A, B, and C, I need to have three different equations. And there are the three equations. Okay, so what's f at 0? 1. What's p at 0? I take 0, I plug it into this equation, I get c. So c is the number 1. What's f prime at 0? Still 1, isn't it? The derivative of e to the x is e to the x. When I plug in 0, I get 1. What's p prime at 0? All right, what's the derivative of ax squared plus bx plus c?
2ax plus b.
2ax plus b. So p prime is 2ax plus b. So when I plug 0 into this, what do I get?
B.
B. So b is the number 1 also. Okay. What's f double prime at 0? It's 1 still, right? What's p double prime? That should be double prime then. What's p double prime at 0? 2a. So a is going to be a half. All right, so this is called, what we just did, this is the second order Maclaurin polynomial for f of x equals e to the x. So let's see how that looks on the calculator. We have 1/2 x squared plus x plus 1. There's e to the x. There's x squared. Does x squared match well? Better. What do you mean by better? Better than linear. It looks like they match up for quite a ways along here. I mean, they look pretty good all the way up until maybe x equals 1, don't they? They match pretty well. How about on the left-hand side? Not so good, right? Why not? Because e to the x goes to the asymptote. This is a polynomial that goes up. But it's better. So the second order Maclaurin polynomial matches better than the first order Maclaurin polynomial. What would be better than the second order Maclaurin polynomial? The third order Maclaurin polynomial. So if I had f of x equals e to the x, And now I want my polynomial to be, instead of using A, B, and C, I think I'm going to use, I think the book uses C. C sub 3 x cubed plus C squared, C sub 2 x squared plus C sub 1 x plus C sub 0. Now I'm looking for 1, 2, 3, 4 variables, so how many equations am I going to need? 4. What are my 4 equations going to be? F at 0 equals P at 0. F prime at 0 equals P prime at 0. F double prime at 0 equals P double prime at 0. And finally, F triple prime at 0 has to be P triple prime at 0. All right, well, what happens when I take 0 and I plug it into this polynomial? I get C sub 0. And what happens when I take 0 and plug it into my function? 1. So 1 equals C sub 0. Seeing a pattern yet? We got 1 the first time, we got 1 the second time, we got 1 the third time. Okay? What's going to happen when I take the derivative of this thing and then I plug in 0? I'm going to get C sub 1. Because when I take the derivative, I'm going to have a 3x squared here. I'm going to have a 2x there. This one's going to go away. But when I plug in 0, that one's going to go away. That one's going to go away. The only thing that's going to survive is C1. I'm going to get 1 equals C sub 1. What happens when I take the second derivative? Well, when I take the second derivative, this one's going to go away with the first derivative, isn't it? When I take the second derivative, what's going to happen to this piece? It's going to go away. Its derivative will be 0. What's the second derivative of this one? It's going to be 2c2. And how about the second derivative of this one? It's going to have a 6c3, but it's also going to have an x, isn't it? Because you're going to take the derivative twice. You're going to bring the power down. That'll be a 3. You're going to take the derivative again. That'll be a 2. It'll still have an x in it. So when I plug in 0, what's going to happen? It goes away. So what's the only thing that survives? 2c2. So 1 equals 2c2, which means c2 is a half. That's the exact same as what we had before, isn't it? 1, 1, 1 half. All right, now how about this last one? When I take the third derivative, this piece is going to disappear. That piece disappears. Third derivative, this one disappears. What's the third derivative of this one? 6c3. 6c3, which means c3 is 1/6. So we get the exact same answer we did before, we just added one more term. Let's see how that one looks. So I'm just going to be lazy here. I'm just going to type in plus 1/6 x cubed. What can you tell me about x cubed? Better still, isn't it? In fact, on the positive side, quite close for a long time now, isn't it? Negative side, it was better. Eventually the x cubed goes down below the axis, but it was better. What would be better than a third order Taylor polynomial? What would be better than a fourth, fifth, sixth, seventh, so on and so forth? All right, so my question to you is there a pattern in these numbers? 1, 1, 1/2, 1/6. What's the next one? 1/24. Where in the world did you come up with 1/24 out of that?
It's a factorial because of the power.
It's a factorial, exactly. think about it, if I started with x to the fourth, I would have to take the derivative 4 times, which means I would pull down a 4, I would pull down a 3, and I would pull down a 2. And then I would pull down a 1. So the number that I would have in front here, taking the derivative 4 times, would be a 24. What if I wanted to do the fifth Taylor polynomial? It would be a 5 factorial. All right, so here's the general rule. The Maclaurin polynomial for f of x is the constant will just be f of 0 plus, then you're going to have the derivative at 0 divided by 1 factorial times x. The next one is the second derivative divided by 2 factorial times x squared. What's the next one? Third derivative divided by 3 factorial x cubed. And you can go as long as you want. In general, what's going to go with the power of x to the n? N factorial on bottom and up on top?
N prime.
The nth derivative, yeah, whatever. Usually we use this symbol.
The last one we would eventually get e to the x.
Well, now we're only doing polynomials, which means n is a finite number. So I might stop at n equals 12. If I use n equals 12, would I get something very, very close to e to the x? Yes. Would I get exactly e to the x? No, unfortunately. But it would be very close. So how do I make it be exactly e to the x? Don't use polynomials. What do you use? No. I use an infinite polynomial. I just keep going and going and going forever. That's not this section, though. That's coming up in the very near future. That's called a Taylor series, where instead of stopping at x to the 12th, you just keep going forever.
So like an infinite limit pattern?
An infinite, one of those things.
Infinite sum.
So e to the x, we will show that e to the x is a sum from n equals 0 to infinity of the nth derivative at 0 divided by n factorial times x to the n. But that's coming up in the near future. That's not for today. That's where we're going to. Okay, so I want you to find, let's say f of x equals, how about sine x? I want the 6th order Maclaurin polynomial. Well, if you're going to give me the 6th order Maclaurin polynomial, what do you need to know? The 6th derivative, and the 5th, and the 4th, and the 3rd. And, all right. So, what I like to do is I like to build a table. And I'm just going to start taking derivatives. I start with sine. What's the derivative of sine? Cosine. What's the derivative of cosine? Negative sine. What's the derivative of negative sine? Negative cosine. What's the derivative of negative cosine? Sine. What's the derivative of sine? Cosine. What's the derivative of cosine? When do I stop? Right now, because there's 1, 2, 3, 4, 5, 6 derivatives, isn't it? So there's my 6 derivatives. Okay. Then for each of these, I have to plug in 0. So what do I get when I plug in 0? What's sine of 0? 0. What's cosine of 0? What's sine of 0? What's negative cosine of 0? What's sine of 0? What's cosine of 0? What's negative sine of 0? 0. Okay, so here's my answer. Sine of x is approximately f at 0. What's f at 0? 0. Put everything in there. We go. F at 0 is 0, so it's going to be 0. Plus, what's f prime at 0? 1. Divided by 1 factorial? That's 1. Times x. Plus, what's f double prime at 0? 0. So I don't need to bother with the rest of it, do I? 0 times anything is 0. Plus, what's the third derivative at 0? So I'm going to have negative 1 divided by 3 factorial x cubed. Plus, what's the fourth derivative? It's 0. Plus, what's the fifth derivative? Back to 1. So that's going to be 1 over 5 factorial x to the fifth. And then finally, plus 0. So, sine of x is approximately equal to x minus 1 over 3 factorial plus 1 over 5 factorial. Oops, x cubed there, x to the fifth there. Just for fun, how good is that? Y equals sine x 1 minus 1 divided by 6 times x cubed plus 1 divided by 5 factorial happens to be 120 times x to the fifth. Let's do a zoom trig. Oh, I hope not. We'll know in a second. Yeah, I'm definitely missing something. How about an x right there? Alright, so there's my sine wave. And there's my polynomial. How well do they fit? Pretty good between, that's not 1 by the way, because I did a zoom trig. That's negative pi over 2 to pi over 2. Pretty good between negative pi over 2 and pi over 2. How can I get it to be better? Yeah, what's the next one going to be? It would be minus 1 over 7 factorial x to the 7th. And then what's the next one? 0. And then what's the one after that? Plus 1 over 9 factorial x to 9. So there's an obvious pattern, isn't there? Only the odd powers survive. Let's just try those two just for fun. Minus 1 over, what's 7 factorial? Yeah, I don't know either. There's a factorial button on my calculator. One over 9 factorial x to the 9th. So by adding 2 more terms, still thinking. Huh?
It's going slower now.
Well, it's doing a lot of calculations. I mean, you divide by 9 factorial. See how fast you are. By adding 2 more terms, notice that we're now pretty accurate from negative pi to pi. So by adding 2 more terms, in a sense, we've doubled our amount of accuracy. All right, so why is this important?
Convert from trig to non-trig.
You guys love using your calculator. When you type in sine of pi over 12 and hit enter, your calculator spits out an answer. How did it get that answer?
That formula.
The calculator had some form of approximation. I don't know that it's exactly this one, but that's how it's doing it. What do you mean, isn't it infinite?
Oh no, because you have the number in there.
Yeah. So just for fun, variables, y function. Oops, I wanted y2, not y1. Sine of pi over 12. Well, how does your calculator compute sine of pi over 12? It has some sort of approximation built in. Notice what happened there. I got exactly the same answers, didn't I? That's how computer programming works. When you get right down to the very basics, what's the only thing a computer can do?
Yes and no answers.
It can give you yes and no answers. So in essence, the only thing a calculator can really do is add. It can take 2 binary numbers that have zeros and ones in it, and it can add them together. So when you get right down to the nuts and bolts of the programming, anything you do in a calculator or anything you come to do in a computer somehow has to come down to an arithmetic, an adding. And that's how your calculator computes sine of pi over 12. It has some sort of approximation in it that allows it to go back to arithmetic. Simple adding, come up with the answer.
Did someone just sit down and think about all that and program that with a calculator?
No, they didn't have to sit down and think about it. Taylor and McLaren thought about it hundreds of years ago. All they had to do was program it in. Taylor and McLaren gave them the answers. All right, well now let me ask you a question. What if I want to plug in 2 pi? What's sine of 2 pi? 0. But what if I take 2 pi and plug it into my approximation? Oops. Not so good anymore. Why not?
It's only good to pi, negative pi.
It's only good for a certain area. So now how is the calculator plugging in 2 pi and getting an answer of 0? Which is the right answer?
Because it's series to the end, and ours is finite.
Probably not.
Can't you like shift it?
You shift it. And that's known as a Taylor polynomial. This polynomial that we created was centered where? Centered at 0. So it would make sense that when I plug numbers into this that are close to 0, I'm going to get a fairly accurate answer. As I get further and further away from 0, what's going to happen to the accuracy of my answer? It's going to get worse and worse. So what do? If I want to plug in 2 pi, I create a different polynomial, no longer called a Maclaurin polynomial, but rather called a Taylor polynomial. So we have a slightly different definition.
Why are the range more accurate? Like if you kept adding numbers.
If I kept adding terms, that convergence, where they're close to each other, would keep getting wider and wider and wider.
Eventually 2 pi would be right.
Eventually 2 pi would be right.
Is that because you're bringing the x closer to 0 by the factorial?
Yeah. The factorial, you're dividing by a bigger and bigger number, which is, you're adding less and less error each time. Yep. So the Taylor polynomial centered at x equals c. F of x is approximately, instead of having f at 0, we're going to have f at c. Plus, instead of f prime at 0, we're going to have f prime at c divided by 1 factorial, and then we won't just have an x here, we'll have x minus c, which is really the same thing we had, but before we were using c equals 0, so we just had x minus 0, which we just wrote as x. Plus, the next one will be f double prime at c divided by 2 factorial times x minus c squared. And you keep going. Plus f triple prime at c divided by 3 factorial x minus c cubed. Plus, you can keep going as long as you want, and eventually you decide, hey, I've done enough derivatives. And there's your Taylor polynomial centered at c. So if I wanted to plug in 2 pi, what I would do is I would create a Taylor polynomial centered at a number closer to 2 pi. So I wouldn't center it at 0, I would center it somewhere else. Alright, so here's an example of that. Let's let f of x equal ln x. Can I center ln x at x equals 0? Can I find the Maclaurin polynomial for that? No, why not? I can't plug 0 into ln, can I? So where are we going to center it? Pick a nice number. Center at c equals 1. I like 1 a lot. And how many derivatives do you feel like taking? 4. So we're going to find the 4th order Taylor polynomial. All right, so we're going to start with ln x. We're going to take the derivative. What's the derivative of ln x? 1 over x, which I'm going to write as x to the negative 1. Then you're going to take the second derivative. What's the second derivative? Negative 1, x to the negative 2. How about the third derivative? 2x to the negative 3. And finally the fourth derivative. Negative 6, x to the negative 4. All right, then we're going to plug in x equals 1. Oh, I didn't build my table right. That's okay. We'll do it over here. What do you get when you plug in x equals 1? What's the ln of 1? 0. Plug 1 in. What's 1 to the negative 1? 1. Plug 1 in. You get negative 1. Plug 1 in. You get 2. Plug 1 in. You get negative 6. Okay, so our answer is ln of x is approximately f at c was 0, plus f prime at c. F prime at c was the number 1 divided by 1 factorial times x minus 1. Plus our second derivative was negative 1 divided by 2 factorial x minus 1 squared. Plus third derivative was 2 divided by 3 factorial x minus 1 cubed. And then finally our last one, our fourth power, we had a negative 6 over 4 factorial x minus 1 to the 4th. Okay, so just cleaning this up a little bit, I'm going to write it as x minus 1 minus 1/2 times x minus 1 squared plus, what's 2 divided by 3 factorial? A third, because 3 factorial is 6. 2 over 6 is 1/3. 1/3 times x minus 1 cubed minus, what's 6 divided by 4 factorial? A fourth. X minus 1 to the 4th. If I kept going, what's the next one? Plus 1/5, x minus 1 to the 5th. The next one? Minus 1/6. They alternate, minus, plus, minus. So that happens with a lot of these. You get working these out and you start to see a pattern in these coefficients. Okay? Questions on that? One other famous one. Some famous Maclaurin polynomials. This ln is one of them. Sine x we already saw. What happened with sine? You got the odd ones. What do you think is going to happen with cosine? Any guesses?
Evens.
You get the even powers. So you get 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial. And how about e to the x? We kind of did that one, didn't we? With e to the x, we got, they were all positive, weren't they? 1, 1, 1/2, 1/6. So we had 1, 1 factorial, 2 factorial, 3 factorial down on bottom. So e to the x, its Maclaurin polynomial, is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, x to the 4th over 4 factorial, and you can keep going. So it's kind of interesting that it looks like there's some very close relationship between e to the x, sine x, and cosine x. Cosine has the odd powers, but they alternate. Or I'm sorry, cosine has the even powers, but they alternate. Sine has the odd powers, but they alternate. E has all the powers, and they don't alternate. Not quite. Because if you add those, you're still going to have the alternating. You'd have a 1, and then you'd have an x, but then you'd have a minus x cubed over 2 factorial, a minus x cubed over 3 factorial. So they're close. They're very close to each other, but not quite the same. Well, remember, it's not that easy. If I take the absolute value here, I have to take the absolute value of the whole thing, which doesn't mean I just get to change that to a plus and that to a plus, unfortunately. So no, that's not quite right either, but you're getting closer.
Is it negative dx?
Nope, we'll figure out what it is later.